Okay, for segment 2, we'll pick up where we left off. We were just about to look at an example where we have examples of force vectors operating in different directions, and we're going to try to find out some things about them, like, for instance, the angle between the forces. The example being used is 3 dogs pulling on a stick in different directions. There's a sketch on page 81 if you want to see it, but it's basically just 3 dogs pulling on a stick. The important thing is that the first dog pulls with a force which we'll call F1 because we're really imaginative. And the force is equal to 10I times unit vector I minus 20.4. That came out a little smudged, so I wrote it up here again. 24.4 times unit vector J plus 2 times unit vector K newtons. That's, of course, remember the SI unit of force. Dog 2 pulls with a force of F2, and that has an equation of negative 15I minus 6.2K newtons again. And dog 3 pulls with force F3, because we just have no creativity at all. That equation would be 5I plus 12.5J newtons. So these are the equations for the 3 forces, and we want to find the angle between forces F1 and F2. So it looks like we might be doing something like this. So first of all, we need to find the components of the vectors F1 and F2. We were given the components actually in the equation. So F1 x component is 10 newtons. The y component of F1 is negative 20.4 newtons, and the z component of F1 is 2 newtons. For F2, the vector F2, the x component is negative 15 newtons, y component is 0, because if you look back at the equation, you'll notice that there was nothing times unit vector j. But unit vector j is not even mentioned. That means basically that unit vector j was multiplied by 0, and that's why it disappeared. So we can assume that the magnitude for the y component is 0. And then the z component for F2 is negative 6.2 newtons. We're only looking for the angle between F1 and F2, and so we don't actually need anything about F3 for this part of the problem. Next, we want to find the magnitudes of F1 and F2 because we need them for the equation to find the angle between them. So remember, the magnitude is just the x component, the square root of the x component squared plus the y component squared plus the z component squared. So that's the square root of 10 squared plus negative 20.4 squared plus 2 squared, which comes out to the square root of, 520.16, and that's 22.8 newtons for the magnitude of F1. For F2, the magnitude of F2, that is square root of the x component squared plus the y component squared plus the z component squared, which is the square root of negative 15 squared plus 0 squared plus minus 6.2 squared. That comes to the square root of 263.44. And when you take the square root of that, you get 16.2 newtons. Okay, so the scalar product is going to be just the, again, the x component of one vector times the x component of the other, plus the y component of one vector times the y component of the other, plus the z component of one vector times the z component of the other. So here, looking at the components, we have 10 newtons times negative 15 newtons plus negative 20. The negative didn't come out too clearly. Negative 20.4 newtons times 0. And 2 newtons times negative 6.2 newtons. Okay, so it's basically just this times this, plus this times this, plus this times this. And when we add that all up, we get negative 162.4 newtons squared, because remember, it's newtons times newtons. So that would be newtons to the second power. That is the scalar product. And now we can find phi, the angle, because the scalar product is equal to the magnitude of one vector times the magnitude of the other times cosine phi. So in other words, cosine phi is f1 dot f2, that is the dot product of the two vectors, divided by the magnitude f1 times the magnitude f2. So it's this divided by this. And that equals negative 162.4 newtons squared over 22.8 newtons plus 16.2 newtons. And that's equal to 162.4 square newtons over 369.36 square newtons, which comes out to negative 0.4397. Notice it's negative because the 162.4 was negative. And also notice that the units cancel because it's square newtons over square newtons. So it's just a number. And that's good because cosines and other trigonometric functions like that are just numbers. They shouldn't have units. So the angle itself is going to be the inverse cosine of that number, because that number is the cosine of the angle. So remember, it helps, or at least it helped me, to think of inverse cosine as the angle whose cosine is. On the calculator, it would be just, if I can get this stupid thing on the calculator, it would be inverse or second function cosine. Notice the little tiny print above the cosine button says cosine minus 1. And that's exactly what comes up on the screen if you hit second function and then cosine. Negative 0.4397 equals 116.08, blah, blah, blah. So we'll call that 116.1. And that's what we got, 116.1. That's the angle between the two dogs. If the unit vector, or if the vectors are given in terms of unit vectors of axes, then we can actually find the angle without any kind of geographic directions. In the last, I think the last dog problem we had, they were saying that, this dog was pulling with this much force to the east, and this dog was pulling to the southwest, and that kind of thing. But I, J, and K give directions also. So you can substitute I, J, and K for, north, south, east, and west just as well. Okay, there is an example for further work where it asks us to find the angle between dog number 1 and dog number 3 in the same situation. And what I would suggest is that you shut off the video, try it, and then pick up where we left off. And then we'll work it out together. Okay, so why don't you give that a try, see what you come up with, don't look, and then we'll come back together in a moment. So shut it off. And okay, if you're coming back now, then we find the x, y, and z components of the two vectors in question. Vector f1 was the vector that we used before, so the x, y, and z components are just the same as the top line here. X component is 10 newtons, y component is negative 20.4 newtons, and the z component is 2 newtons. For F3, the original equation said was 5I plus 12.5J, and nothing said about K, which implies that K must be 0, or that is, the magnitude of K must be 0. And so we come to the X component of 3 is 5 newtons. The Y component of F3 is 12.5 newtons, and the z component of F3 is 0. Okay, we don't, because we're only going for the angle between F1 and F3, that means we don't need any info about F2. So because we're only concerned about those two vectors, we don't need anything about the other one. So the magnitudes of these two vectors, well, we already found the magnitude of F1 up here, where it came out to be 22.8 newtons. And so we don't have to do that again. But you could, if you want practice. F3 is just going to be the square root of the x component of F3 squared plus the y component of F3 squared plus the z component of F3 squared. And that's square root of 5 squared plus 12.5 squared plus 0 squared. And that is the square root of 181.25, which is 13.46. And I squeezed in the end there. Hopefully you can see it, for newtons. Okay, newtons, because it's a force. As before, we need to do the dot product of the two vectors. And so F1 dot F3 is just the x components of F1 and F3 multiplied by each other, plus the y components multiplied by each other, plus the z components multiplied by each other. So that's 10 newtons times 5 newtons plus negative 20.4 newtons times 12.5 newtons plus 2 newtons times 0 newtons. And so that's 50 newtons squared plus negative 32.9 newtons squared plus 0, or 17.1 newtons to the second power. And to find the angle, again, the dot product of F1 and F3 would be equal to the magnitude of F1 times the magnitude of F3 times the cosine of the angle between them. You want to solve for the cosine of the angle between them. So that's dot product of F1 dot F3 over the magnitude of F1 times the magnitude of F3. We just found what the dot product is, 17.1 square newtons. And the magnitude of F1 we already found was 22.8 newtons. And the magnitude of F3 we found just a minute ago was 13.46 newtons. And when you multiply these together, you get 17.1 newtons to the second power over 306.9 newtons to the second power, and that's 0.0557. Again, units cancel, and it's just a number, which it should be because cosines are just numbers. The actual angle is going to be the inverse cosine. In other words, the angle whose cosine is 0.0557. So again, on the calculator, second function, cosine 0.0557 equals 86.8 degrees. Okay, and you could, if you wanted to, go back and do the same kind of thing to find the angle between dogs number 2 and 3, which I think is the only combination we haven't found yet. And you can see how that works out. The next example is about work and force, kind of introducing a bit of a new concept, but it is still working with dot products. So when a force on an object, force is a vector because it has a magnitude and a direction. So force acts in a direction. Like when I was first explaining the difference between mass and weight, I mentioned that weight is a force. It's a downward force because it's caused by gravity pulling on your body's mass. And so that force has a direction. But you can exert forces in other directions too. If you lean against a wall, you're exerting a sideways force on the wall. If a force acts on an object and it causes a displacement of the object, which is also a vector, then work is defined as force times distance. generally in physics, that's how it's stated, force times distance. But again, this is another case where we're dealing with displacement or distance in a straight line. So displacement, the magnitude of displacement, that is the same as the distance. And so you can think of this as force times distance, but technically it's force times displacement. And it's actually a dot product. I used an X here because this is the way it's often written in physics when you're not dealing with vectors. But when you're dealing with vectors, this is the way it's written. Work, which is usually symbolized by a W, equals vector F dot vector D. So force dot product with displacement. Working with the dogs again, going back to that last example where we had dog number 1, dog number 2, and dog number 3 pulling on the stick with a certain force, with each of them, and the equations for the individual forces were given in terms of the unit vectors. If actually that previous example was done assuming that the stick didn't move, because if it moves, then that's a whole other set of problems. And in this case, though, we're assuming that the stick does move and that its displacement, which is a vector, has the equation minus 7.9 unit vector j minus, or plus or minus 4.2 times the unit vector k centimeters. And then the question is, how much work is done by dog number 3? Okay, so looking back, we'll recopy the equation for the force vector for dog 3. That was 5 times unit vector I plus 12.5 unit vector j newtons. So remember, capital N in this case means newtons, not north. And the displacement, which we were just given, is minus 7.9 j minus 4.2 k centimeters. So the work of dog number 3, which we'll call W3, is just vector F3 dot vector D. So that's, again, it's just the x coordinates times the y coordinates, or x coordinates multiplied together times the y coordinates multiplied together, or plus the x coordinates of the two vectors multiplied by each other, plus the y coordinates multiplied by each other, plus the z coordinates multiplied by each other. Okay, so the x coordinates for F3, the x coordinate was 5. For D, you notice there's no I in this equation. So that implies that the magnitude of I must be 0. So x component of F3 times the x component of D would be 5 times 0. So that's nothing, it drops out. The y component of F3 is 12.5 newtons, and the y component of vector D was negative 7.9 centimeters. And so we have 12.5 newtons times negative 7.9 centimeters. And then for the z components, for F3, you'll notice there's no k term, which implies that the magnitude of k must be 0. So that's going to be 0 newtons times negative 4.2 centimeters. So that entire term becomes 0 and drops out. When we multiply this out, we end up with negative 98.75 Newton times centimeters, or Newton centimeters for the units. That is a valid unit for work. The units for work are units of force and distance. And Newton is a unit of force and centimeter is a unit of distance or displacement. So that is a proper unit. But the usual units for work are joules, which are also units of energy, because work is a form of energy, actually. And a joule is a Newton meter, not a Newton centimeter. So if we want to change Newton centimeters to Newton meters, we can leave the newtons alone. We just have to change centimeters to meters. So we could take negative 98.75 Newton centimeters times the fact that there's 1 meter for every 100 centimeters. Centimeters will cancel out. And if so, numerically, you're just taking negative 98.75 divided by 100, which is negative 0.9875 Newton meters. Or in other words, negative 0.9875 joules. Okay, so that's finding it in the more, the more proper units of joules. A further example, that's the amount of work done by dog number 3, sorry. Dog number 3. Further examples would be how much work would be done by dog 1 and dog 2. And again, don't look, I'm going to have you, I suggest anyway, that you shut off the video and try those two things. And then we'll come back in a moment and compare results. Okay. And in fact, our first segment ran a little too long on the video, so I'm going to cut off this second segment video here and pick up the solution to this question in the third segment in just a moment. Okay, so try the problem and then start segment 3.